Lecture 8 covers sections 3.1, 3.3, and 3.5. At the end of today's lecture, you should be able to apply the formulation of work and heat to closed systems. For us to begin, let us recall the conservation of energy equation. The COE states that our change of energy, dE, is equal to the change of our internal energy, dU, plus the change of our kinetic energy, dKE, plus the change of our potential energy, dPE. And this is equal to our heat supplied less our work done on our system. This tells us that energy within a process or cycle has to be conserved. We can neither create nor destroy energy. And the energy is a point variable, as represented by a full derivative d. It is evaluated between our initial and final states. However, our work and heat terms, delta W and delta Q, both still have path dependence, and the difference of delta Q and delta W gives us a point variable, dE. Before we get into path dependence in the subsequent evaluation, which will be the basis of lecture 9, let's look at each term of our conservation of energy equation. From physics, we recall that work is defined as a force F acting through displacement x. That is, we can move from point 1 to point 2, such that the displacement is in the direction of our applied force. We say delta W is equal to F dx. To solve for our work going from point 1 to 2, we'd integrate from point 1 to 2 our force with respect to dx. And we'd have units of joules, or Newton meter. Now, in thermodynamics, work has a more general meaning. Work is done by a system if the sole effect on the surrounding could be the movement of mass. This doesn't mean we have to move mass for us to do work. Now this seems odd, right? If we're not moving mass, how are we doing any form of work? Well, energy can be added in the form of heat, and this reflects original experiments done by Joule. A paddle wheel was inserted into a fluid, which was connected to a pulley, and a weight, which was positioned above the ground. The weight was released, the paddle wheel was spun, and he measured the change of temperature of the fluid. Based upon the change of energy, i.e. the change of the potential energy, he was able to measure the change of temperature within the system. This was due to viscous dissipation. All fluids have some internal friction associated with them. Or, our conservation of energy states that such energy is transferred across a system boundary. That is, we can have electrical work crossing a system boundary as well. Now, work done by a system is going to be an output and quantified by a positive value. Work done onto a system is going to be input, and it's a negative value. Now, power, W dot, is a time rate of change of work. W dot would be equal to delta W per delta T, which would have units of joules per second, or watts. Now, we can also have work on a per mass basis, i.e. our specific work, which is equal to our work going from state 1 to state 2 per the mass. Now, everything we formulated thus far is for a fixed boundary control surface. It's not going to be valid for a moving boundary control surface. Now let's look at an example of the application of our work equation. In our first part of this example, we want to consider a piston cylinder device that's filled with an ideal gas. The initial pressure inside the device is 0.2 MPa, and it has a volume of 40,000 cubic centimeters. If heat is added such that the volume increases to 100,000 cubic centimeters, we want to calculate the amount of work done on the system. And we are going to assume that this occurs underneath a constant pressure process. Then, for the second part of this example, we want to imagine our device contains 0.5 kilograms of ammonia at minus 20 degrees centigrade and a quality of 25%. If we add heat to increase the temperature to 20 degrees centigrade, where our volume increases by a factor of 1.4 and our pressure linearly increases with volume, we want to determine the work produced. Let us begin by considering part A. Now, if we proceed from state 1 to state 2 in a constant pressure process, we need to express our formulation of work in a thermodynamic perspective. Recall work from state 1 to state 2 is equal to integral from 1 to 2 of F dx. Now, force is pressure times area. So we'd have the integral from state 1 to state 2 of PA dx. Now, for a piston cylinder device, our area is constant. And area times dx, i.e. the change of distance of our pistons with respect to initial position, will give us dV, differential volume. Thus, we can say our work from state 1 to state 2 is equal to integral from state 1 to state 2 of PdV. If our pressure is constant, it moves outside the integral, and our integrand is unity. So our work from state 1 to state 2 for a constant pressure process would be equal to our pressure times the change of volume between our final and initial state. For this problem, our pressure was given as 0.2 MPa or 200 kPa, and our change of volume went from 100,000 cubic centimeters at state 2 from 40,000 cubic centimeters at state 1. So we'd have 0.1 minus 0.04 meters cubed. Thus, our work produced within this process is 12.0 kilojoules. The quantity is positive, and therefore we have work out of our system. Now for part B, we have to first look at state 1. We have a temperature of minus 20 degrees centigrade and a quality of 25%. Thus we are existing at saturation temperature and pressure. If we consult table B.2.1 to look at our saturated ammonia, we can see our pressure at state 1 is corresponding to our saturation pressure of minus 20 degrees centigrade, and our pressure is 190.2 kPa. Our specific volume at this state would be our saturated liquid specific volume plus our quality times the difference of our saturated vapor and saturated liquid specific volume. Thus, our specific volume corresponding to state 1, where we had a temperature of minus 20 degrees centigrade and a quality of 25%, would be 0.15696 meters cubed per kg. Now we know at state 2, our volume is 1.41 times that at state 1. So our specific volume at state 2 would be equal to 0.2213 meters cubed per kg. Now at state 2, we'd recognize that our specific volume is close to that at 600 kPa. And this is seen on table B.2.2, our saturated ammonia tables with our pressure entry. Now we have to evaluate our expression for work. That is, our work going from state 1 to state 2 would be equal to the integral from state 1 to state 2 over pressure times our change of volume. And our change of volume can be equal to our mass times the change of our specific volume. Our mass is constant, and this will come outside the integral. Since our pressure increases linearly with respect to volume, we're going to take our average pressure. That is P1 plus P2 per 2. And this will be an average value that is outside our integral. Thus, we'd have P, average, times our mass, times the integral from state 1 to state 2 of unity, d nu, which is just the difference of our specific volume between state 2 and state 1. So our work from state 1 to state 2 would be equal to m times the quantity P1 plus P2 times the quantity nu2 minus nu1 per 2. If we substitute in our values, we have a mass of 0.5 kilograms, our pressure at state 1 is 190.2 kPa, and our pressure at state 2 is 600 kPa. Our specific volume at state 2 is 0.2213, and our specific volume at state 1 is 0.15696 meters cubed per kg. And thus, this particular configuration is producing 12.71 kilojoules of work.